Download this code from codegive.com, link in the description below. An introduction to Cisco queuing and QoS, prioritizing network traffic. This tutorial provides a comprehensive introduction to Cisco queuing and quality of service, QoS, explaining the underlying concepts, different queuing mechanisms, and how to configure QoS on Cisco devices using practical code examples. What is QoS and why is it important? Quality of service, QoS, is a set of technologies and mechanisms that allow network administrators to control and manage network traffic to ensure critical applications receive the resources they need to operate effectively. It prioritizes different types of traffic, ensuring that sensitive applications like voice and video experience minimal delay, jitter, and packet loss. Why do we need QoS? Bandwidth limitations. Network bandwidth is a finite resource. Without QoS, all traffic competes equally for this resource, leading to congestion and performance degradation. Application sensitivity. Some applications, like VoIP and video conferencing, are highly sensitive to delay and packet loss. Even minor disruptions can significantly impact their usability. Other applications, like email and file transfers, are more tolerant. Improved user experience. By prioritizing critical applications, QoS ensures a smoother and more reliable user experience. Business critical applications. Many business applications require high availability and low latency. QoS guarantees that these applications receive the necessary resources. Compliance and regulatory requirements. Some industries are subject to regulations that mandate specific QoS levels for certain types of traffic. Key QoS concepts. Congestion. Occurs when the volume of traffic exceeds the capacity of a network link or device. This leads to packets being queued, delayed, or even dropped. Delay. The time it takes for a packet to travel from its source to its destination. Excessive delay can make real-time applications unusable. Jitter. The variation in delay between packets. High jitter can disrupt audio and video streams. Packet loss. Occurs when packets are dropped due to congestion or errors. Significant packet loss can make data unreliable and applications unusable. Bandwidth. The capacity of a network link or device to transmit data. Classification. Identifying different types of traffic based on various criteria, such as source and destination IP addresses, port numbers, or application protocols. Marking. Assigning a specific priority or class of service to a packet. This allows network devices to recognize and treat the packet accordingly. Queuing. Organizing packets into different queues based on their priority. Queues are serviced in a specific order to ensure that high-priority traffic is processed first. Policing. Limiting the amount of traffic that can be sent from a particular source. This prevents a single source from consuming excessive bandwidth. Shaping. Smoothing out traffic flow to prevent bursts of traffic that can cause congestion. Shaping delays packets to conform to a defined rate. Congestion avoidance. Mechanisms to prevent congestion before it occurs by proactively managing traffic flow. Congestion management. Mechanisms to deal with congestion once it has occurred, such as queuing and packet dropping. QoS models. Best effort. The simplest QoS model. All traffic is treated equally, and no prioritization is applied. This is the default behavior on most networks. Integrated services. Serve a per-flow QoS model that reserves resources for specific applications. It requires signaling between devices to establish and maintain reservations. Int-serve is complex and not widely used in modern networks. Differentiated services, diff serve a more scalable QoS model that classifies traffic into different classes of service. Each class is assigned a specific priority and treated differently by network devices. Diff-serve is the most common QoS model used in modern networks. Diff-serve building blocks * traffic classification * identifies traffic based on certain criteria and assigns it to a specific class. * traffic marking * sets a specific value in the IP header to indicate the class of service. The most common fields used for marking are *DSCP, differentiated services code point, a 6-bit field in the IP header that is used to indicate the class of service. It replaces the older TOS, type of service, field. *IP precedence * a 3-bit field in the IP header. While still present for backward compatibility, DSCP is the preferred method. *COS, class of service a 3-bit field in the 802.1q VLAN header that is used to indicate the class of service on layer 2 networks. Traffic policing / shaping * controls the amount of traffic that can be sent or received, preventing any single source from overwhelming the network. Congestion management * determines how traffic is handled when congestion occurs, using queuing and scheduling mechanisms to prioritize different classes of traffic. Congestion avoidance * attempts to proactively prevent congestion by monitoring traffic levels and taking action to reduce congestion before it occurs. Cisco queuing mechanisms * Cisco routers and switches offer a variety of queuing mechanisms for managing network traffic. Some of the most commonly used mechanisms include FIFO, first in, first out, the simplest queuing mechanism. Packets are processed in the order they arrive. Offers no prioritization and is not suitable for QoS. PQ, priority queuing divides traffic into multiple queues, each with a different priority. High priority queues are serviced before low priority queues. This can lead to starvation of low priority traffic. It's considered obsolete. CQ, custom queuing allocates a fixed amount of bandwidth to each queue. This provides a degree of fairness but can be difficult to configure and manage. It's also considered obsolete. WFQ, weighted fair queuing allocates bandwidth to each queue based on its weight. This provides a more flexible and fair allocation of bandwidth than CQ. WFQ is generally configured automatically. CBWFQ, class-based weighted fair queuing extends WFQ by allowing you to define traffic classes based on various criteria, such as IP addresses, port numbers, or application protocols. Each class is then assigned a weight, and bandwidth is allocated accordingly. CBWFQ is widely used for QoS. LLQ, low latency queuing combines CBWFQ with a priority queue. This allows you to prioritize delay-sensitive traffic, such as VoIP, while also providing fair bandwidth allocation for other traffic. LLQ is considered the gold standard for QoS implementation. Cisco QoS configuration steps * 1 classification * define traffic classes based on specific criteria. 2 marking * mark packets with appropriate DSCP or COS values. 3 queuing * configure queuing policies to prioritize different classes of traffic. 4 policing / shaping * implement policing or shaping to control traffic flow. Cisco QoS configuration examples * Scenario *. Let's say we want to prioritize VoIP traffic on a router interface. We want to ensure that VoIP traffic receives the lowest possible delay and jitter, while other traffic is handled with lower priority. Assumptions asterisk. Asterisk VoIP traffic uses UDP port range 16,384 to 32,767. Asterisk the interface we're configuring QoS on is Gigabit Ethernet 0/0. Asterisk we are using DSCP values for marking. Code example asterisk. Explanation asterisk. Asterisk class map defines traffic classes based on match criteria. Asterisk VoIP traffic matches traffic using the RTP protocol and UDP port range 16,384 to 32,767. The match protocol RTP command intelligently identifies RTP traffic based on header inspection. Asterisk data traffic matches any traffic. Since it uses match any, it will capture all traffic that doesn't match previous classes. Asterisk policy map defines the QoS policy and specifies how to handle different traffic classes. Asterisk QoS policy is the name of the policy. Asterisk class VoIP traffic configures QoS for the VoIP traffic class. Asterisk priority %30 creates a priority queue, LLQ, and allocates 30% of the interface bandwidth to this class. This is crucial for ensuring that VoIP traffic receives preferential treatment. Using % allocates a proportion of available bandwidth. You can also use a fixed bandwidth value with priority kbps. Asterisk police CIR %30 BC 1000, policing enforces a maximum rate for VoIP traffic. CIR stands for committed information rate, which is the allowed rate. BC stands for burst committed and represents the maximum burst size that's allowed. Asterisk class data traffic configures QoS for the data traffic class. Asterisk bandwidth remaining %70 allocates 70% of the remaining bandwidth, after VoIP traffic is served, to this class. This ensures fair allocation of bandwidth among data traffic. Asterisk random detect DSCP based, enables weighted random early detection, WRED, based on DSCP values. WRED is a congestion avoidance mechanism that proactively drops packets based on their DSCP value when congestion is detected. This can help prevent congestion and improve the performance of delay-sensitive applications. Asterisk interface Gigabit Ethernet 0/0 applies the QoS policy to the output direction of the Gigabit Ethernet 0/0 interface. Service policy output indicates that the policy is applied to outgoing traffic. Marking at the edge, optional. The additional code snippet illustrates how to mark VoIP traffic with the DSCP value F, expedited forwarding, at the network edge if the endpoints themselves cannot mark the traffic. This is often necessary in environments where the VoIP phones or applications are not configured to mark traffic. Asterisk class map match any VoIP marking defines a class map to match VoIP traffic based on RTP protocol and port range. Asterisk policy map marking policy defines a policy map to mark the traffic. Asterisk class VoIP marking configures the policy for the VoIP marking class. Asterisk set DSCP F sets the DSCP value to F, expedited forwarding, DSCP 46. This tells downstream devices that this traffic should be treated with the highest priority. Asterisk interface Gigabit Ethernet 0/1 applies the marking policy to the input direction of the Gigabit Ethernet 0/1 interface. Service policy input indicates that the policy is applied to incoming traffic. Important considerations asterisk. Asterisk bandwidth calculation asterisk carefully calculate the bandwidth requirements for each traffic class to ensure that critical applications receive sufficient resources. Monitoring monitor the performance of your QoS policies to ensure that they are working as expected. Use commands like show policy map interface to monitor traffic statistics. Network-wide QoS QoS is most effective when implemented consistently across the entire network. Oversubscription avoid oversubscribing the bandwidth of your interfaces. QoS can only help manage congestion, it cannot create bandwidth. MTU considerations when using QoS, make sure that the maximum transmission unit, MTU, is configured correctly. Larger MTU values can reduce overhead but may also increase the risk of fragmentation. End-to-end QoS ideally, you want to have end-to-end QoS, meaning that QoS is implemented on all devices along the path between the source and destination. This ensures that traffic is consistently prioritized throughout the network. Testing thoroughly test your QoS policies to ensure that they are working correctly and that they are not negatively impacting other applications. Advanced QoS features shaping smooths out traffic flow to prevent bursts of traffic that can cause congestion. Useful for controlling traffic sent from a network edge. Policing with conform/exceed/violate actions. Allows you to specify different actions to take based on whether traffic conforms to, exceeds, or violates a defined rate. Marking based on application recognition. NBAR allows you to classify and mark traffic based on the specific application being used. Verification and troubleshooting. Show policy map interface displays statistics for the QoS policy applied to a specific interface. This command is invaluable for monitoring traffic levels, packet drops, and queue utilization. Show queuing interface displays detailed information about the queuing configuration on an interface. Debug QoS queuing enables debugging of queuing events. This can be helpful for troubleshooting problems with queuing. Use with caution as it can generate a large amount of output. Ping and trace route with QoS options. Use these commands with QoS options, example DSCP values, to test the end-to-end performance of specific traffic classes. Conclusion. This tutorial has provided a comprehensive introduction to Cisco queuing and QoS. By understanding the underlying concepts and implementing the configuration examples, you can effectively prioritize network traffic, improve application performance, and enhance the user experience. Remember to plan your QoS policies carefully, monitor their performance, and adjust them as needed to meet the changing needs of your network. Always test your configurations in a lab environment before deploying them to a production network. Good luck.